Good morning, everyone. I hope you guys are having a good start to your Tuesday. I hope that you had a good weekend. Today is the 16th, and we are 1 week away from the review that we're going to be doing for our first test. So I wanted to share my screen and show you kind of where we are. And I'm going to go ahead and do the student view. So in case you're like, oh, well, I want to, navigate through any other parts of the page. So this is our homepage for our course. Today is the 16th. Later today, I'll be posting our lecture recording. We've got the PowerPoint, PDF, and one thing that I added, I think that was on Thursday or Friday, was this learning objectives link. So if you click on this link, you'll be taken to this page, which kind of brings up like the big questions for the day. And so if there's something where you're like, oh, we talked, what did we talk about? Well, it's these five major things for today. And when you click on any one of these links, they'll take you to a YouTube video that corresponds to that content. Many of these videos are from a guy named Tyler DeWitt or from Khan Academy, or just any other what I think is like a substantive and good link. So it's like an extra review option for you. Now, in addition to that, if you're ever like, well, I want to navigate to other parts of the semester, you can always click on this View All Pages link, and that's going to take you to all of the pages that have been published. And so, welcome August. That shows our August calendar. And if you remember, that was pretty short. We only had two class meetings. So if you're ever like, oh, I need to find my old stuff, it's going to be there. And the reason that I did this, and I hope that it worked out. My plan was just to kind of make it so you weren't looking at a semester's worth of dates and topics at any given time. Instead, you could kind of jump back and forth and say, okay, well, what are we focused on right now? And I decided to just divide it up by months. So September is the landing page for our, currently, because that's what we're in. Um, so I can go back to September. The PowerPoint that we're going to work on, or the slide deck that we're going to be working with today, is this ions one. And then on Thursday, we're going to be talking about bonding. There's learning objectives there. My goal and my plan is to get through all of the stuff for Thursday. Sorry, back to September. Get through all of this so that next Tuesday, the 23rd, will simply be a review. It's entirely possible that there might be something that I want to finish up from this bonding stuff on Tuesday the 23rd. But my plan and my intent is for that just to be kind of like wrapping up odds and ends. Now, in addition to that, one of the things that I posted yesterday, and I will continue to add to, is if you go to quizzes, you'll see practice exam number one. Right now, that only has 11 questions on it. I'm going to be adding more and more to that. And this will just give you kind of a test run of what it's going to be like. What are the questions that you should be able to answer? Um, you have 999 attempts to use to do this, to practice this. If you need more than that, let me know. And this is going to be open for the remainder of the semester, so that you'll be able to, before the final exam or before the next module exam, you'll be able to try that again. But those are kind of the major announcements. So what I'm going to do is I'm going to go ahead and get started on talking about ions. Now, our objectives for ions, or our learning objectives for kind of this module, first of all, I want you guys to be able to know what is the charge of an ion based on the number of electrons, based on the number of electrons it has. So if I were to say something like potassium ion, I want that to mean something to you. So then you say, okay, well, what is potassium? Oh, I know that potassium has the symbol of K. And I know that looking at the periodic table, I don't remember it at the moment, it has 16 protons. That could be an incorrect number. So I want to clarify that. Okay, well, based on that, and this specific ion that I'm asking about has 17 electrons, I'd want you to say, oh, well, that has a -1 charge because it has more protons than electrons. So that's one thing that we're going to get through. Then I want you to know and be able to kind of have muscle memory to say, what's the charge of a neutral atom? And how might I identify a neutral atom without saying the neutral atom of blah? So I want you to know that. What's the difference? What's the major difference between an atom and an ion? Based on symbol and charge, what is an atom or ion's electron configuration? That electron configuration is 1s2, 2s2, 2p3, and so on. Then, how does a Lewis dot symbol change based on charge? Okay, so we haven't yet talked about Lewis dot symbols, but the rest of this, we've kind of, it's almost like I've spilled out the Lego pieces on the table and I've said, okay, well, here, grab this piece, this piece, this piece, and we're going to assemble it into lots of these learning objectives. Now, the first thing is, I mentioned this last class period. This is our first poll question. I'm going to go ahead and open this up. Oh, nope, end poll. Nope, that only has three answer options. Oh, I got to edit this one. Dang it, I thought that it had more. No. What about this? There. Well, that's got five, but we'll go with it. Um, so which one of these is a metal? Carbon, lead, both, or neither? And if you've got a periodic table before you or nearby, which you can always go to ptable.com, that's the letter P, table.com. We talked about kind of the organization of the periodic table and how you can identify a metal or a non-metal. Okay, well, I'm going to go ahead and end this poll in about 5 seconds. Three, two, one, zero. Okay, so the majority of people, we're looking at 75% of the class answered B, lead. And you're absolutely correct. Now, one of the things that I was alluding to with respect to looking at the periodic table is your metals are on the left side, whereas your nonmetals, Nm, are on the right side of the periodic table. So that's just kind of a almost slipped out of my chair. That's a good general rule of thumb that you can use and follow as okay, if you ever need a reference point or if you're kind of stuck on one. Generally the left-ish side. All right. Now, a conductivity test is a way that you can also kind of differentiate between a metal and a nonmetal. Now, on the left-hand side, what I want you to notice is that we've got some pencil lead here. So we've got a battery that has a current running to a light, through this light, to this pencil lead or graphite, and then it goes back through the battery. So this battery is sending an electric current, and essentially, if these two banana clips, I think those are banana clips, if those were directly connected to one another, this light would be completely illuminated. You'd have no issue seeing that light. Now, the question is this conducting electricity? Is there an electric current that can run through that? The no's are pretty accurate. If you look closely, you can see that it's kind of illuminated, but that's one where you can kind of say, you can grade it on kind of a spectrum, and you can say, well, yeah, McKinsey's got it with a little. It kind of conducts. So we could go ahead and say that graphite or a carbon molecule, this non-metal, is kind of a weak conductor of electricity. Not super strong compared to aluminum foil or Al. Well, that aluminum foil is just a bunch of aluminum atoms. So it's aluminum atoms, and lo and behold, it's a very strong conductor. So this metal, and I'll go ahead and say this metal strongly conducts. So the electric current flows through the metal, goes to the light, and we're good. Now, what are kind of, so whenever I was mentioning the left versus the right-hand side, a fair question is, okay, well, where do you divide these? And the way that we divide them is basically by silicon, germanium, antimony, polonium, tellurium, arsenic, silicon. Think about these as your dividing line. These, this dividing line or this group of elements that are our dividing line, these are metalloids. So that means they have properties similar to metals, but properties similar to nonmetals. So then if I circle this side, this left block, and actually, you know what, just to be a little bit more precise, you know, boron. I sometimes I'm looking at my own periodic table right now. Oh, you're absolutely right. I skipped over two of those there. I apologize. Um, I got a private message. Boron? Yes, boron. Okay, boron, silicon, germanium, antimony, polonium, and oh, not polonium, astatine. Joel. Goodness gracious. Yeah, silicon, germanium. I'm gonna do individual lines. Germanium, antimony, tellurium, astatine. Okay. And then arsenic is one, and yeah, it's good there. Okay, there we go. Those are our metalloids. These have properties similar to metals, but properties similar to nonmetals. So astatine, tellurium, antimony, arsenic, germanium, silicon, boron. Now, the big circle, those are our metals. And my big circle there, not particularly drawn well because it also includes these and it also includes these. But I hope that you kind of get the picture with my left-hand side. Now, the right-hand side, which I'm going to change colors to do that, and I'm going to say green. These are nonmetals. So your metals are going to be good conductors of electricity. They're going to be good conductors of heat. Your nonmetals, weak conductors or non-conductors. Now, your metalloids are pretty interesting and pretty cool because if you think about, let's just take iron, just as an example. Iron is smack dab in the middle right here. Oh, good morning. I'm not sure, but my computer wasn't letting me submit an answer. The screen for the question went away when I tried to click an answer. Is there any way I can still review? There's going to be additional questions, so just hang out and wait for those and make sure that you answer those. Okay, so iron is a strong conductor. Okay, it conducts electricity. It also conducts heat. If you put a piece of iron on your stovetop and let it heat up over time and then you touch it, well, it's going to burn your hand. Now, If you remove that from the heat source, it's going to retain that heat for a long time. You touch it, after 5 minutes, it's still going to burn your hand. So it's a strong conductor of heat. In addition to that, iron's a strong conductor of electricity. Whenever an electric current's running through something, what happens to what happens to a metal that is conducting electricity over time? While it conducts electricity, what will it ultimately do? Think about touching it and what I was just saying. It's going to heat up. Okay, those two are going to go hand in hand with a material like metal. Now, with that in mind, we've got this substance right here. I'm putting a circle around. Silicon. Silicon is a metalloid. So it has properties of metals, but properties of nonmetals. Okay. A nonmetal is not going to conduct heat. It's not going to conduct electricity, either of those things very well. A metalloid, silicon, can anyone add to the chat, whenever you've heard the word silicon, what have you heard it in the context of, or what has it been related to? Computers. Absolutely right. Not plastic surgery, silicone, C-O-N-E. That's a different material. Silicon. Don't worry about it. Happens. I'm happy that we had that because silicon, SILICON, is what is used for microchips. Yeah, silicone is different. Now, silicon is great for conducting electricity. Hmm. So yes, we've had a poll question. We're going to have more. So whenever I use my phone, there's silicon in here that's conducting electricity. There's also some metal in here, but there's electricity that's being conducted through silicon microchips. Now, if let's say that rather than silicon, my phone had nothing but metal conducting electricity, and I put it to my ear, or heck, if I held it in my hand, what's going to happen after, let's just say, like 5 minutes of it being on? Ooh, ooh, exactly. It's going to get hot. Now, silicon, by contrast, well, I can have lots and lots of electrical charges running through this device, and my hand doesn't burn. Do phones ultimately get hot eventually? Yeah, if you leave the screen on for a long time, something like that's going to happen. But my point is that metalloids, they kind of use the positives of a metal and mix them with some of the positives of a nonmetal to give us a different material altogether, or a different kind of result altogether. Now, that's what I want you guys to know for the layout of the periodic table. This line with your metalloids, and then this group for your nonmetals. So as a review, our metalloids: boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. If you're on the right-hand side of that, it's a nonmetal. If you're on the left-hand side of that, it's a metal. Now, the next thing that I wanted to get into was drawing Lewis structures and Lewis dot structures. Now, the point of a Lewis structure is to display or give a symbolic representation of an atom and its valence electrons. So could anyone add to the chat, what are the valence electrons? Outer. Yeah, your outer electrons, the ones that are kind of the farthest out. Now, with that said, if we jump back a slide, could anyone tell me, add to the chat, how many valence electrons let's go with bromine have? How many valence electrons does bromine have? I got a private message of 7. You're absolutely right. Now, how many total electrons does a neutral bromine atom have? 35. 35 is correct. Okay, so remember our valence electron number is coming from the second digit in our group number. Our total number of electrons is 35. Okay, so let's jump back. So if we wanted to draw a Lewis symbol to represent these two atoms, aluminum and phosphorus, I'm going to jump back just so that question that came into the chat, will we be provided with a periodic table for the exam? Yes, you will. Now, aluminum. How many valence electrons does aluminum roll in with? 3, because it's in this group. Boom, 3. So we want to draw those 3 to represent this. And, you guys aren't going to have to draw this as a part of an exam, but you will have to identify this. Now, one thing that I want to kind of start out with is if I'm drawing 3 valence electrons for aluminum, where I'm going to start is on the right-hand side of my atom or of my symbol. So now I have 2 left to do. So then I'm going to draw my other one on the left-hand side. My third electron is going to go up top, and there is my Lewis structure for something with 3 valence electrons. Now, what I want to clear up is if somebody draws it like this, and this is obviously not an exam, but if they were to draw it like this, am I going to hold that against you and be like, oh, -5? No, I'm not. In addition to that, exam questions that you should anticipate, I'm not going to say like, hey, which is the correct structure for aluminum, A or B? That, to me, that's a little bit like missing the point of the exercise and of learning this. Because in this case, you understand, or actually in both models, you understand that it has 3 valence electrons. Okay, now phosphorus. Phosphorus is rolling in with a grand total of 5 valence electrons. And so what we're going to do is we're going to start on the right, go to the left, go to the top, go to the bottom, and then our 5th one, we're going to draw on the left-hand side. So kind of for our second dots, we're going to start on the left and go clockwise. So this is the model for phosphorus. Now, what is important about all of this? And if I were to like rank like most important things, I would say number 1, correct number of, I'm going to say E like that, valence electrons, though. That's what I'm kind of getting at. Correct number of valence electrons are drawn. The second item is, well, even distribution. And what I mean by that is, here is a reasonable question that I could ask you, or that I might ask you, is I'll give you, which is the correct symbol for aluminum? And I'll say A, and then I'll go with B, and then I'll just throw a third one down here. B looks like that. There's no electrons, no valence electrons drawn. C looks like this. The grand total of electrons that we're going to draw surrounding our symbol is we're going to draw a maximum of 8. And so the way that I always kind of visualize this is something that I don't actually draw, but it's helpful kind of as like a mental like overlay. As I think about, I put my symbol in a square, and then on each side I put a maximum of 2 dots. Now to illustrate that idea and apply it to other Lewis symbols for our main group elements, here's what we've got. We've got hydrogen with just 1 electron, 1 valence electron. Hydrogen happens to only have 1 electron. Cesium down here. Well, cesium is a group 1 atom, has 1 valence electron. Bromine, chlorine, fluorine, and iodine, lo and behold, they have the exact same number of valence electrons. And their symbols all look very similar to one another. The only difference is what are the letters that make up the symbol. Then our noble gases, all of these, starting with neon and going to xenon, well, they've got 8 electrons around that symbol. Helium has 2. Now, that's because let's think about the electron configuration of helium. 1s2. Helium has a 1s2 electron configuration, and it's happy as a clam. Lithium, well, it has one valence electron. And what do we know about lithium and that one valence electron? What is it like to do? Or what is it kind of easily going to do? It's easily going to lose that one valence electron. And whenever it does, then it only has 2 electrons. And then effectively, it has the same electron configuration as helium. Now, those are bringing in a couple of different concepts. They're kind of converging. And I want to pause right there, or pause right there with that topic because we're going to revisit it. Now, I'm going to open up another poll question. So here we go. This poll question is now, wait a minute. Oh, wait. Stop sharing. Launch. Okay, there you go. How many dots surround B in the Lewis symbol for boron? Go ahead and answer or put your answer into the poll question. And I'm going to go ahead and draw this one out. So we've got B, and then boron. I jump back. Well, boron it's in group 3. It has a total of 5 electrons, but only 3 of them present. Okay, I'm going to go ahead and end this. We've got 89% of the class answered correctly with B as the correct answer. So good job, everyone. Or good job, 89% of the class. Okay, we'll move on from there and introduce this rule known as the octet rule. And the octet rule states that, just a second. The octet rule states that atoms are going to, or they tend to gain, lose, or share electrons until they have 8 valence electrons. Now, that's kind of your goal to get to 8 valence electrons. Now, I want to show you guys this table again. Tell me which group of atoms has 8 valence electrons. And maybe not every single one of them, but most of them have 8 valence electrons. Noble gases. What was the word that started with an S that we use to describe our noble gases? Stable. So basically, it's when you think about your noble gases and you think about this octet rule, what is every atom kind of trying to do? They're trying to gain, lose, or share electrons to reach some sort of stability. When they get to 8 valence electrons, whether it's by sharing or donating or losing or something like that, they're kind of reaching that level of stability. Now, what I want you to think about here is let's look at potassium. Potassium's a group 1 metal. Now, as a group 1 atom, what does actually here I'll present it as 2 different options. Potassium can A, gain 7 electrons, or B, lose 1 electron. Now, I want you to think about this in terms of what do you think is going to be easier, not necessarily the result. So, Kelly, I agree completely. It's easier to lose one electron than it is to gain seven more. It's almost like, well, I don't know. But it's easier to lose that one electron. Now, with that in mind, can anyone tell me what atom potassium will then have the same electron configuration as when it loses that one electron? Give me the symbol. Ar. Argon. You're absolutely right. Because if we look at the periodic table, and I'm going to go back just a second. When we look at the periodic table, here's potassium. Potassium has 19 protons, 19 electrons when it's a neutral atom. Now, potassium can either gain seven valence electrons, and then if it does, it will have the same number of or same valence electrons as krypton. Okay. Or it can lose one, and then it has the same electron configuration as argon. When it loses, when potassium loses one valence electron and it gets to basically this right here, and I know that I'm drawing them out of the sequence that I said to draw them in. I apologize for that. When potassium loses one electron and then it has this situation right here, what's that word that we said? Starts with an S. It has now kind of achieved stability. It's stable. Now, with that in mind, it's stable, but do you think that it has a charge? Y or N, does it have a charge? It does. You're absolutely right. Because did the number of protons change? Nope. So this still has 19 protons, but now, since it lost one electron, it's only got 18 electrons. Now let's think about that for a second. Now, on one hand, you've got your noble gases, argon. Argon has 18 protons, 18 electrons. It's happy. But where are those protons? They're found in the nucleus. Those protons that are found in the nucleus, well, they're not moving. They are stuck there. Same thing goes with potassium. Potassium has 19 protons, and they're stuck in the middle of the nucleus. What are those 19 protons doing to all of the electrons that potassium has? Well, they're kind of attracting them. They're trying to pull them in as much as possible. So effectively, potassium has just a greater number of protons than it has electrons, and potassium's going to have a positive charge. Is that a problem? No. Its electron configuration is a stable electron configuration, the same as argon. Now, if we look at something like bromine, bromine's got two options. Bromine can either gain one electron to then have the same electron configuration as krypton, or it can lose seven and then have the same electron configuration as argon. Well, it's easier just to pick up one to attain that noble gas configuration. You've got a little bit of an imbalance of the protons and electrons, but there's more stability that's kind of achieved by gaining one more electron. And that's is gaining one electron versus gaining seven electrons. Those are different animals altogether. So what that means ultimately is stuff on the left-hand side, your group one and group two metals, they tend to lose electrons. Stuff on the right-hand side, they tend to gain electrons. Now, one thing that I want you to recognize is, well, I drew a big circle, and I'm going to go ahead and add in some more things. These guys all tend to, so carbon, nitrogen, silicon, and phosphorus, they tend to gain electrons. Boron and aluminum, they present an interesting situation because aluminum tends to Well, lose electrons. And boron, it actually, this is an exception to the octet rule. And what I mean is that that boron isn't looking to get, you know, five more electrons. It's not looking necessarily to get to eight electrons around it. Boron is actually happy with six electrons around it. Okay, now some examples of this kind of playing out. This right here is sodium, and this right here is chlorine gas. Now, chlorine gas has historically in humanity or like in humanity, I think it was in World War One, chlorine gas was used as a chemical weapon. Sodium, this metal, if you had pure sodium, does everyone and actually go ahead and give me a one or a two? One in the chat if you can see that these things right here are different than this substance right here. And two if you don't see the difference between them. Okay, so these things on the left-hand side, the chlorine gas and sodium, they're different than sodium chloride. If you took this substance right here and threw it into a body of water, it'd light on fire. It's very volatile, very, very extreme. Chlorine gas is something that is potentially hazardous and deadly. If you mix them together, they make your steak taste a little bit better. Or they make French fries. There we go. I like French fries. Best fries in my book, P. Terry's. Um, so you've got your sodium chloride, potentially dangerous long term based on diet and other factors. But in terms of acute damage that it can cause to you, nothing compared to what sodium and chlorine do. Now, this is planting a seed for Thursday's class, but um, what did I, could anyone spell out this substance right here? I called it chlorine. Could anyone spell that out for me? Chlorine. 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 Yes. Okay, great. And would anyone agree that that's what that, okay. Yeah, yeah, good, 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 good. Then this combination, sodium, chlor, could anyone finish that word or finish that phrase? Sodium chloride. Chloride. Okay. Now, I want to plant this seed that those are different. And it is significant because we're going to be learning and talking about nomenclature on Thursday and naming and why you name things certain things. But for the time being, I just want you to be like, they're different. I know that they're different. Okay. So when you react sodium and chlorine gas with one another, this sodium has one valence electron. And you know what it does? It says, I'm going to be selfless. Chlorine, you can have that one valence electron. And chlorine says, oh, you're so thoughtful. You're so generous. Thank you very much. Um, but where does that leave you? And sodium says, well, it's pretty good for me because I've lost an electron and I I have this positive sign because I'm a positive ion now. And so I'm good there. And then chlorine, you've accepted that electron and now you have a complete octet and you have a negative charge, but that's just because you have an imbalance of protons and electrons. And the chlorine says, yes. And I now have a new name, and my new name is chloride. And sodium says, that's great. I'm happy. We've worked this deal out. Sodium says, I give you an electron. Chlorine says, I'm going to gladly take that electron. And they both have different charges. Now, what that looks like, here what we have is a difference. Na and Na plus, Cl and Cl minus. When you just write out Na or K or Cl or Br, when you just write out the symbol, this corresponds to the atom. None of these have a charge. They are all neutral. So if I were to give you a blanket question, or sorry, if I were to give you a question of which of these is an ion? A, B, C, and D. Your answer would be B. Now, if I were to instead say which of these is an atom, well, that would be A, C, and D. Now, the difference between them is A, C, and D. What's the charge on all of those? A, C, and D. What is the charge on A, C, and D? Neutral. They all have the same number of protons and electrons. Their numbers of protons and electrons cancel one another out. So a sodium atom has 11 protons, 11 electrons. A sodium ion, by comparison, well, it's got 11 protons and it's got 10 electrons. Because what happened? Well, it lost one electron. Now, this is one example of a sort of table that you might have to, or you might see on an exam. And the way that it would show up on an exam would be something like, what number goes in the empty space? And then you just have to select, oh, well, I'm going to use this because it's got a symbol, a lettered symbol plus a charge. Okay, so that tells me how many. Okay, well, it's positive. If it has 11 protons, then since it's positive, it must have 10 electrons. Now, with that in mind, let's think about the electron configuration of this. What is the electron configuration of Na plus? Okay, the electron configuration, if you remember, oh, wait, I'm sorry, I missed your question, Kelly. Could it have fewer than 10 electrons? Okay, I'm going to jump back. I'm pumped about that question because that is a fantastic question. The answer is it's complicated. Um, in terms of, well, how likely am I to hear of that? How likely does a chemist ever see a sodium ion with less than 10 electrons? I would say basically never. So the answer is kind of no. But if you're asking from the standpoint of, well, hypothetically, if you're just giving us a question on an exam and it had fewer than that, well, things would change. If I change the symbol from Na plus to Na3 plus, well, then what would you put in the electrons column? Is you'd say 8. Now, how likely is that to occur? Very unlikely because if we think about sodium, when it loses one electron, it then has the same electron configuration, a little bit of a spoiler here, the same electron configuration as neon. What do we know about the electron configuration of neon as a noble gas? I'll give you a hint, it starts with an S. Stable. So as soon as an ion is formed that has an electron configuration equal to a noble gas, it's stable. It doesn't want to lose or gain any electrons. It's good to go. Does that help? Great. Happy to hear that. Okay. So now with that in mind, what is the electron configuration of sodium? Now to break this information out a little bit, you're correct. It is the same as neon, but how do we kind of reassemble it? Well, this is going to require a little bit of recall. But for our noble gases and for every single atom has one s2. After that 1s subshell has two electrons in it, then we go on to the 2s subshell. And it's 2s, okay? The s subshells can hold a maximum of two electrons. So 1s2, 2s2. We can add those exponents. 2 plus 2, that's 4 total electrons. We have a total of 10 electrons that we need to account for. So that's when we bring in the 2p subshell. That 2p subshell, can anyone tell me in the chat how many electrons can the 2p subshell or a p subshell hold? Absolutely, 6. 2p6. Am I good? Y or N based on that? Yeah, absolutely. So there's our electron configuration of a sodium ion, Na+. Now, another question that I think is good to think about is, well, of this electron configuration, of that whole electron configuration there, which electrons are our valence electrons? Could anyone add to the chat the the subshells that have our valence electrons for this? And I'm looking for numbers and letters. We've got the noble gas or neon's electron configuration. So what's neon's valence electron configuration? We've got 8Ne. Okay, I like that. Neon, we're right. Our 8 electrons. We've got Maddie, you are right on the cusp of it. We've got to get to 8 though. So adding that exponent, the 6 to 2s. So if I said which subshell has our valence electrons, this would be 2s2, 2p6. Does that make sense? Y or N to the chat. Okay, great. Now, we're going to go on from there. This is a ion that is pretty much not going to exist, but I think that it's a good exercise. What is the electron configuration of Na minus? Okay, Na minus, that's not going to really form, but we've got the same thing. Na minus, that's an additional electron. That is not going to have 10 electrons, but instead it's going to have a grand total of 12. So we've got 1s2, 2s2, 2p6, and then last but not least, 3s2. So now a question related to this would be, which are our valence electrons? Our valence electrons here would be just the 3s2 valence electrons. So I want you to be able to kind of, oh, Victor, or sorry, somebody sent me a private message. Could you also write it as Ne3s2? Absolutely. When you use that condensed notation with the nearest noble gas, you could say Ne and then 3s2. Great question. That's absolutely right. All right. Now, what's the electron configuration of chlorine minus? Cl minus. Okay, so that's where we've got an additional electron for chlorine. Chlorine has 17 electrons. 17 electrons when it's neutral, add one more. So 1s2, 2s2, 2p6. So that gives us 10 electrons accounted for. And now the next 8 are going to be our valence electrons. How do I know it's the next 8? Well, the way that I know it's the next 8 is because where is chlorine on the periodic table? Well, it's right here. When chlorine picks up one more valence electron, it then takes on the electron configuration of argon. Now, to look at this, rather than on this slide, but to look at it on the periodic table, what we're looking at is this right here. And again, I've kind of written all over this, but chlorine picks up one more electron. It has argon's electron configuration. So going back, doop, doop, doop. There we go. So I'm going to go ahead and put a bracket underneath because now I'm filling in my noble gas, or sorry, my valence electrons. 3s, 2, and then 3p6. I have 18 electrons, 2, 4, 10, 12, 18. Is that what the minus means? Absolutely. This minus, that minus right there indicates that we're talking about a charged atom, also known as an ion. We have an we have a imbalance, or we don't have the same number of protons as we have electrons. So that negative there indicates that we have one additional electron than we have protons. So just to kind of let's go, I'm going to look at the periodic table, and I'm going to throw some answer options or some questions at you. Add to the chat, how many electrons does Se 2 minus have? Total electrons. How many total electrons does Se 2 minus have? The correct answer is 36. Okay. Because now what I want you guys to do is add to the chat, how many total electrons does Se have? 34. So a selenium atom has 34 electrons because whenever I use that term atom, I'm talking about it being neutral. Se2 minus, well, it has two more things that are negatively charged. Electrons are negatively charged, so that gets us to 36 electrons. What about Se plus 5? Or 5 plus? Use those interchangeably. 29. Because what that means is we've lost 5 electrons. This is one of the trickiest parts about chemistry, is just keeping straight, like, wait a minute, I've gained something that has a negative charge. Oh, I've added a negative. Ooh, that throws people for a loop. SB 3 plus. How many electrons does SB 3 plus have? Total electrons. 48. Great job. 48 is the correct answer. Because, or actually, I'll go with smaller numbers. Li 3 plus. How many electrons does Li 3 plus have? Try to visualize, how many protons does Li 3 plus have? Well, Li has 3 protons. Yep. If it has 3 plus, each one of those protons, positive, 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 there are no electrons there. It doesn't have any electrons to cancel them out. So what I think is a helpful exercise, and I will give you a question like this on the exam. I'll PT plus 3. Before you answer that, your process should be, okay, well, PT plus 3. PT is right here. I found it on the periodic table. When it's neutral, it's got 78 protons. And it's got 78 electrons. Okay. So that would give me 0. If let's go in one direction. Let's say I had 81 electrons. Electrons are negatively charged. Protons are positively charged. That would mean I've got, that would be PT 3 minus. A couple people sent me the private message of 75. You're absolutely right. So it wouldn't be 81 electrons. Instead, it'd be 75 electrons. All right. Now let's go back to where we were. Okay. So Electron configuration for Cl plus. Well, Cl plus, that's going to have not 18 electrons, but 16 electrons because it's going to have a positive charge, one more proton than it has electrons. So we're talking 1s2, 2s2, 2p6. That's 10 electrons. Now we've got our valence electrons, 3s2, then 3p. Ooh, okay, so that's 2, 4, 10. So I added 2 plus 2 plus 6 is 10, plus 2 gives us 12, plus 4 gets us 16. All right. Now, when we're talking about building an atom, I think that it's helpful to go ahead and give you this poll question. Let's relaunch this poll. Yes, because this one only has 3 answer options. Relaunching, that's fine. Okay. This represents what? A neutral atom, a positive ion, a negative ion. And I think that it's helpful to look at this right here and account for your subatomic particles. 3 protons, 3 neutrons, 2 electrons. Protons are positive. Boom, boom, boom. Electrons are minus, minus. Okay, I'm going to give about 5 more seconds. And that's going to do it. All right, so the correct answer is a positive ion because we have more protons than we have electrons. So 56% of the class marked B. And the next popular answer was neutral atom. And then the next was negative ion. All right, so if you're thinking, well, I did it right. How did I get the wrong answer? Here is our key. Protons are the orange balls. 1, 2, 3. So we've got 3 plus. Some of you guys are accounting majors, so try to look at an accounting problem. Electrons. 1, 2. 1, 2. So that's 2 minus. So if you add that together, you end up with plus 1. Now, when it comes to atoms and ions, neutral atoms, positive ions, negative ions. Neutral atoms have an equal number of protons and electrons. Positive ions have lost electrons. That has happened. Positive ions have more protons than electrons. Negative ions have gained electrons, and they have more electrons than they have protons. We've got a poll question here, and go ahead and put your answer in. How many dots surround Br in the Lewis dot symbol for Br minus? Think about the maximum number, and then looking at the periodic table, how many does Br have? And then whenever you add an additional electron, what does that get you? I'll give you a hint. It's not A or D. I'm going to leave this up for about 5 more seconds. And scene. Okay. So the correct answer is 8, C. When we've got Br minus, Br has 7 valence electrons. It gains 1 more. We're up to 8 valence electrons then. So 8 is the correct answer. Another poll question. How many total electrons are in Br minus? Answer this poll question. If you miss a poll question, I'm sorry. We've had, let's see, like 5 questions today. So, and remember, you just got to get 2. How many total electrons are in Br minus? If you need, toggle back to the periodic table. And I'll just leave this one open and continue the lecture. So when it comes to total electrons in Br, let's see, let's look at the periodic table. Br has an atomic number of 35. So it's rolling in with 35 electrons right there when it's in its neutral state. Whenever it has a 1 minus charge, we're looking at have a total of 36 electrons. So the correct answer for this one is none other than, oh, there we go, D, 36. Okay, I'm just going to leave that one up because that's going to be the last poll question of the day. Once you answer it, great. Common ions, there are important common ions that you know because there are some trends. One thing that I want you to know is group 1, what do they like to do? They like to lose 1 electron. Whenever they do that, they get to your noble gas electron configuration. They have a complete octet. Group 2, they lose a pair of electrons to get to that noble gas configuration. And that's for almost all of them. Then on the right-hand side, these tend to gain electrons. These non-metals, they'll pick up an electron and get to that noble gas configuration. Fluorine gains 1. Chlorine, bromine, iodine, they all gain 1 electron to get to that noble gas configuration. One of the reasons that I think is helpful to learn electron configuration is because then you can say, okay, well, 2s, or actually, let's erase that. You can say S2P6. That's what everything wants to get to. On the left-hand side, you're going to lose electrons in order to get to that. On the right-hand side, you're going to gain 1, 2, or even 3 electrons to get to there. Now, with that in mind, what we will commonly see is oxygen and sulfur gaining 2 electrons. Something like nitrogen, what it's going to do is, let's go back to our definition of the octet rule. The octet rule says that we can, there we go. Atoms tend to gain, lose, or share electrons until they have 8 valence electrons. So there are some things like when we talked about sodium and chlorine. Well, chlorine gained an electron. I'm going to ask you, is this electron right here, when we look at this model or this combination, is that electron, would you describe that as being shared by both sodium and chlorine? Add a Y or N to the chat. And just actually, sorry, pump the brakes on your answers. Think about it like this. This is the before, and this is the after. This electron right here and this kind of Lewis structure corresponds to a form of sodium that is violent. That will, if you add it to water, it's going to violently react. Now, can you give me a 1 if you follow and understand that? Okay. Now, this right here is a form of sodium. It's a sodium ion that it's not going to violently react with water. This electron, what I'm kind of getting at is you never have to worry about, if you get a glass of water and you add salt to it, add sodium chloride to that water, you never have to worry about it spontaneously reacting violently. You don't have to worry about it accidentally setting on fire or anything like that. This sodium ion will not just accidentally revert back to this form. It's not going to just easily pick up this electron or get that electron back. And what I'm getting at there is that this electron isn't being shared. This electron was donated to. This arrow right here indicates that sodium said, I don't need this electron. In fact, I don't want this electron. Chlorine, you can have it. So chlorine has basically gained that electron, whereas sodium lost that electron. Can you give me a Y or N to the chat if you follow that? Okay, wonderful. Now, that's what we're looking at here. Looking at this table, I think that it's fair to say, oh, well, which ones do you want us to know? I want you to know the left-hand side and the right-hand side. The stuff in the middle, and the right-hand side includes Al3 plus. The stuff in the middle, these are known as your transition metals. These transition metals like Fe2 plus and Fe3 plus or Cu2 plus and Cu plus. Those have a number of different oh, everyone's participated in the poll. Great. Um, though there are a number of different ions that will be attained there. So I don't want you to commit those to memory. But those on the right-hand side and the left-hand side, I want you to know those. Okay. And that's going to actually call it. That's going to be it for the day. So I'm going to go ahead and stop my recording. I will be joining my office hours link in just a few minutes. I'll probably do it a little bit before 11.